Complete specification based on provisional specification number 12710-76. Title: Numerically Controlled Multifunction Machine Tool Claim, Incorporation of several numerically controlled machine tools, 1, Boring Machine 2, Broaching Machine 3, Drilling Machine 4, Grinding Machine 5, Hobbing Machine 6, Horizontal Milling Machine 7, Vertical Milling Machine 8, Relieving Machine 9, Shaping Machine 10, Turning Machine. Subordinate claims: 1, Automatic Speed Monitoring Units 2, Hydraulic Crankshocks 3, Indexing Mechanism 4, Relieving Mechanism 5, Shifted Belt Conical Pulley System 6, Worm Actuated Shaping Mechanism. Patent Agent and Inventor, Mr. Eric Agate. Market Potential. This numerically controlled multifunction machine tool concept would be of interest to establishments such as research laboratories, maintenance and prototype building workshops that have different tasks to be done in confined space like small laboratories, submarines, ships, mines etc. These exemplarily sited establishments often require high-quality parts, though of different machining approach. The cost of this machine would be in the region of twice that of double spindle machining centers. It is also expected that not many parts of the machine would lie idle at a given machining time since certain parts line the headstock and carriage are nearly always in use. Only the milling head and tailstock could at times lie idle. But even 10 distinct conventional machines are not or would not be in use always. Therefore, it can still be compared to an NC machining center with a coping attachment. A machine part currently idle could be used for mounting the next job or for retooling or for minor servicing. Figure 1, Pictorial impression of the NC multifunction machine tool design concept. Operational configuration. Constituent machines configuration of operational parts. 1. Boring for round work, the workpiece is held on the chuck and the carriage traverses the tool. For boring blocks, for example engine blocks, the workpiece is held on the carriage table and the tool is held and activated by tailstock spindle or milling head spindle. 2. Broaching work is held on headstock chuck and automatically indexed while broach is actuated by the shaping ram, in such case only a single stroke is required. 3. Drilling drill may be held in the normal center lathe style or by the vertical milling spindle, while the work is clamped on the carriage table. 4. Grinding crankshaft is held between centers, while the grinding wheel is held on the horizontal milling head arbor. 5. Hobbing hob is fitted on the milling head horizontal arbor, while indexing of gear blank is provided by the indexing unit via the headstock spindle chuck. 6. Milling. Horizontal, cutter is fixed on the horizontal milling head arbor, the workpiece is held between centers or on the headstock chuck, or on carriage table. 7. Milling. Vertical, the tool is held by a vertical milling head spindle and the workpiece is clamped on the vertical table. Traverses are provided by both carriage and milling head. 8. Relieving work is held on the chuck, cross slide is attached to the carriage reciprocating flange actuated by relieving rod. The indexing unit determines the divisions and coordinates with a numerical control tape reader. 9. Shaping work is held on a chuck or clamped on a table, a reciprocating ram turret head holds the tool. 10. Turning work is held chuck or between centers. Tools are controlled and held by the turret block. Traverses are done by carriage. Machine structure. The numerically controlled multifunction machine is supported on a rigid, horizontal, hardened and ground prismatic bed with smooth finish guides along which feed components traverse. The machine is fixed on robust cast iron plinths of about 200 mm in height. The main unit is fixed on the bed around the chuck section. In this respect, the headstock is supported on robust prismatic cast iron plinths on which an extensional flange for mounting the machine bed projects. The headstock is constructed to accommodate primary components such as the main machine motor, driving mechanism, indexing unit, screw drive, that replace gearbox functions in conventional machines. The numerical control cabinet and electrical panel are also fixed on the headstock to facilitate simultaneous machine control. A multi-purpose carriage slides along with the smooth finish bed guides. The bed guides are fitted with plastic telescopic guards to ensure clear movement surfaces that are free of chips, coolant etc. Tailstock is provided between the bed guides. The tailstock spindle operates primarily within a program code that corresponds to the headstock spindle code. Simultaneous modes of operation are selected as desired to facilitate universal crankshaft grinding. This unit is independent of headstock functions and can be coordinated to suit varying demand of production. The unit has a motor for both shaping and boring operations. The tailstock can be mechanically clamped, shifted, or attached to the carriage for resultant motions. 2 heavy-duty support guides on either side of the machine stabilize the movement of the overhead, hardened prismatic ram. The milling unit traverses along with this prismatic ram. A milling head traverses along the overhead ram guides. The milling head has a motor and driving assemblies encased inside. The milling head facilitates horizontal milling, vertical milling, and universal grinding. The hydraulic control circuits are connected to the hydraulic monitoring unit that is actuated by both the electrical and numerical means. A positive flow hydraulic pump assembly is fitted with a relief valve to ensure the safety of the pump even when most circuits are deactivated. The lubricating system is powered with a pump and is provided with connections to the parts of the machine with running gears. The main bearings for high torque and stress loads should be lubricated with special synthetic lubricants that last for a period greater than 5 years. An auxiliary tray is fitted below the machine bed. A coolant relief system is provided with a pumping chamber beneath the tray. Quill travel. Numerical control system. The NC system is an automated system that consists of analog numerical converters working in binary code. Signal pickup devices convert the block format instructions on punch tapes in absolute or incremental numerical form with reference to the designated origin of coordinate axes. Measurements by working machine parts are represented within a range of 0.01 to 0.1 mm. Digital indicators are provided on the control panel so that the operator can ascertain the tool positional contour and allow the operator's intervention. Photoelectric pickups of 10 tracks decode the block format instructions on punched tape or disc and activate electromagnetic clutches, actuators and valves. The transmitted electrical measurements of the punch tape are thereby converted into signals. Every emitted signal, depending on the measuring code, can represent a linear displacement of either 0.1 or 0.01 mm of the designated coordinate axis. The measuring process is based either on the hydraulic fluid flow or on the lead screw pitch. Electrohydraulic elements derive their displacement values from the rate of fluid flow into hydraulic cylinders in terms of cubic millimeters of fluid. Measurements are monitored by the command memory via sensors. Preparatory interval encoded on the punched tape allows certain machine parts to be locked while new reference positions are selected. That is, achieved by the UN punched intervals of a block format tape. Thus, the preparatory interval is remedial of backlash errors that would otherwise render measurements inaccurate during an automatic cycle. Gear cutting block formats should be programmed under coordination with indexing systems and according to the dividing indexing range stored on the punch disc. The punch disc in an indexing cycle is used instead of a programmed indexing tape. The punch disc is actually an accessory that assists the numerical indexing cycle. They work together during indexing functions. With exception of crankshaft regrinding operation, and under efficient programming of the numerical control system, the machine can enable up to 3 different functions in certain cases. For a motor vehicle workshop, for instance, a set of pre-programmed tapes could be provided for particular workpieces and the operation would then entail replacing the pre-programmed tapes to suit the workpiece to be done. Other modes of controls are the incremental passover system, incremental continuous pass with both circular and linear interpolation, and absolute measurement type of control. The tailstock may have a local electrical control at an easy reach to facilitate local functions. To the remote end of the machine bed, a vertical prismatic column is fixed and fitted with an overhead sliding guide for the longitudinal displacement of the milling unit along which the x-coordinate of the milling processes is provided by a hydraulic system. The hydraulic unit is mounted in the headstock cross bracket. Telescopic guards are fitted along each of the guides. The numerical control tape is punched by means of automatic computer-controlled machines. The main control system comprises 3 tape readers within a cabinet. Every memory tape reader is allocated specific duties: A. Milling operations, B. Turning operations, C. Tailstock operations. Program tape should be a 10-track format with a 30 mm width. Block addresses and operation code should be isotype with even parity. The entire numerical control system of the machine is complex and needs a qualified NC operator because the control system incorporates 3 tape readers, 1 main electrical control panel, 2 sub-control panels and numerous levers and hand wheels. Hydraulics. Hydraulics plays an important part in the automation and drive of the machine. It serves both mechanical and control functions and has mostly been used instead of electromagnetic actuators. The hydraulic pump is a positive flow gear type with a relief valve. The tank, hydraulic cylinder, is fitted in the lower part of the headstock and a pump, strainer and main supply unit are located around it. The supply unit located inside the compartment serves the main hydraulic circuits leading to the main components such as tailstock, headstock, milling head and carriage. At every connection point of the main pipes, secondary supply extensions lead to actuating cylinders, valves and selectors. Each pipe is the double-line type and features fluid supply and return pipes discharging the fluid to the tank via negative pressure strainers. The relief valves enable even a few hydraulic circuits to be used without choking the system. Measurements and motions. In numerically controlled machines, measurements and motions determine the machining quality. Traverse measurements are determined by a punch tape reader. For very accurate programming, an electromagnetic impulse may be designed to represent a measured displacement ranging from 0.01 to 0.001 mm. Electrohydraulic measuring is taken in terms of cubic millimeters of fluid charged to a traverse cylinder. For a high-quality product, the machine is designed with fast working motion, faster approach motion and fastest return motion. These movements are executed by both traversing and rotating components. At the same time, safety and functional stability are provided by rapid locking of components. Figure 4, NC electrohydraulic diagram. Headstock. The headstock is the main part of the machine and is the datum of certain machining functions such as main spindle rotation, indexing and traverses. The spindle's rotational power is derived from a motor, initially by application of a split pulley system, thus the initial speed variation part. Subsequent and major speed control is automatically, numerically, performed by the contra-conical pulley-shifted belt system, consisting of a pair of similar conical, hollow, cylinders fixed in opposite alignment and vary the speed by means of lateral displacement of the drive belt. The lower pulley is driven by the above-mentioned system of split pulleys in the lower headstock casing. The first pulley is designed as a fluctuating, spring-loaded assembly to facilitate belt shifting by lowering the belt tension. The belt tensioning mechanism is electrohydraulically activated and permits entirely automatic speed monitoring. No sooner is the belt tension relieved than the speed monitor shifts the belt from one position to another within a range of the initially selected speed. The whole system works by varying the drive pulley to driven pulley diameters. The resultant of these double speed variations gives the desired spindle speed, from which another set of split pulleys is used to determine the speed of the screw-driven traverse feed. Thus, the cutting speed depends on the spindle speed ratio. Both of these resultant speeds are depicted by means of speed indicators on the control panel. Within the headstock, the cavity is an electromagnetic selector, designated to select the spindle either for turning or for indexing purposes when gear cutting is desired. During such an operation, the spindle's revolution only drives the lead screw and torque is not conveyed to the work chuck. Figure 2, Headstock Plan Sectional Detail. Headstock Plan Parts. 1. Selector fork collar. 2. Durable rubber encased canvas V-belt. 3. Motor spindle. 4. Grill cover to permit airflow into the motor cavity. 5. Shifting belt by speed monitor mechanism. 6. Heavy-duty AC motor, with a range of 30 to 40 kW. 7. Fixed, driven hollow aluminum conical pulley. 8. 80T-driven spur gear, selector, spindle. 9. Electrohydraulic valve to hydraulic assisted parts. 10. Electrohydraulic valve to MH longitudinal screw drive. 11. Worm gear mechanism for indexing selection. 12. Electrohydraulic valve to milling head screw drives. 13. Hydraulic master cylinder. 14. Electrohydraulic valve to carriage screw drives. 15. Electrohydraulic valve to tailstock screw drives. 16. Hydraulic system inspection door. 17. Hydraulic gear type pumping motor. 18. Electrohydraulic valve circuit box. 19. Bearing studs. 20. Tapered roller bearings. 21. Work spindle chuck camlock. 22. Swivel bracket. 23. Bronze bearings. 24. Indexing rate, split pulley system. 25. Head workpiece buttons control box. 26. Controlling screen. 27. Indexing electric control switches unit. 28. Motors starter and control unit. 29. Circuits busbar unit, for mains. 30. Fluctuating rod, electrohydraulically actuated. 31. Bottom conical pulley spindle slide line, guides. 32. Worm gear tilt mechanism for selector fork. 33. Angular revolve rod. 34. Spring shock absorber for motor vibrations. 35. Motor casing. 36. Variable speed selector, fork rod. 37. Angular advancing, work spindle bevel gear. 38. Gunmetal bearing housing. 39. Stud wheel. 40. Indexing split pulley. 41. Manual speed varying device, hand wheel. 42. Miter spiral gear assembly. 43. Worm gear transmission. 44. Speed varying V-belt. 45. Pulley plate adjuster fork, on collar. 46. Main machine spindle. Figure 3, headstock side sectional detail. Headstock side parts. 1. Fluctuation allowance. 2. Fluctuating connector, rod. 3. Hydraulic assisted fluctuating unit. 4. Varying belt, connecting motor to lower conical pulley. 5. Conical pulley, fluctuated to relieve belt, tension. 6. Split pulley positioning, fork, collar connection. 7. Swivel fork pad. 8. Centralized fluctuated spindle. 9. Brass liner for no 8. 10. Triple start, drive belt, speed monitor activated. 11. Fluctuating part, spiral compression spring. 12. Fixed-driven conical pulley. 13. Main machine spindle. 14. Durable shifted belt. 15. Telescopic guards for longitudinal displacement. 16. Longitudinal traverse, hydraulic servo drive cylinders. 17. Conical spindle tapers 1 to 3. 18. Speed monitor, linking spur gear. 19. Tapered roller bearings. 20. Bearing race cover plate. 21. Similar to No 1622. 80T screw drive feed spur gear. 23. 80T spindle driven gear. 24. Splined portion of work spindle, for selector hub. 25. Spiral indexing worm gear 60T on triple start worm. 26. Electromagnetic, conical friction two-way clutch. 27. Dividing indexing worm gear 60T on triple start worm. 28. Split, pulley speed varying adjustment fork assembly. 29. Driven split pulley, final drive for the lead screw. 30. Gunmetal bearing case. 31. Milling transverse alignment guides. 32. Milling head functions, stabilizing guides. 33. Bearing. 34. Chuck head swivel, and miter bevel gear assembly. 35. Work chuck camlock flange. 36. Bearing alignment. 37. Indexing speed control selector fork. 38. Selector fork, the tilting pivot assembly. 39. Section drive, V-belt. 40. Head screw bearing and speed indicator casing. 41. Servo, drive lead screw for carriage traverses. 42. Cast iron plinth frame ribs. 43. Sectioned rib. Tailstock. A tailstock is an independent unit with its own motor. It can be shifted along the machine bed. The motor is enclosed in the casing and manufactured with extension spindles on either side. To the far left, a set of a split pulley system is designed to vary the shaping speed. This speed assembly also has a numerical speed monitor for speed variations. Within the lower compartment of the speed unit, a flexible transmission shaft with a double universal coupling joint is introduced. This shaft derives its power from the motor and in turn drives a recycling pinion within the hypoepicyclic gear. The resultant of hypoepicyclic loci facilitates alternating change of rotational direction every half rotation, 180 degrees. Simultaneous alteration of direction is stepped up by a unit that increases the speed sixfold. After the conversion by this system, the initially unidirectional rotation is converted into numerous counter and clockwise cycles, universal rotation. The universal rotation is transmitted to a heavy-duty triple start worm along which an interlocked half-nut, slider, reciprocates. A robust angular tilting bar tilts about a pivot that is hydraulically shifted. The mount is pivoted on the reciprocating half-nut. This mechanism provides an alternative shaping mechanism. It looks advantageous to the common bull gear quick return mechanism. The length of the bar is made variable to enable automatic adjustment of the shaping stroke by means of the hydraulically shifted, pivoted mounting. The connection to the shaping ram is also similar to the one mentioned above, except that the mounting pivot is also shifted hydraulically to adjust the length of the ram. This concept is novel and constitutes a subordinate claim. The shaping ram tool head is designed with a 6-way turret clapper box, similar in operation to the carriage turret head, and enables the selection of the required tool at different machining stages. On the opposite side of the shaping power source, a different set of split pulley assembly is mounted with a speed monitor mechanism. The speed monitor enables the tailstock spindle rotations to correspond with the headstock spindle rotations when desired. Otherwise, the spindle is independent and can be used for boring, machine center work and for other operations. The tailstock control panel accommodates an electromagnetic clutch button. This determines the function of the tailstock at a specified time, thus, either the shaping ram or the work spindle can be engaged at a time. A speed step-up selector is mounted near the chuck, inside the tailstock cavity. This system enables a two-way speed rating, whether the spindle rotation is required to be high or low, according to the type of job involved. When a bulky workpiece has to be supported by the tailstock spindle, the speed of the headstock and tailstock spindle should match, and be monitored by the numerical controls via respective speed monitors. Only after an initial selection of speed rating, high or low speed, is achieved. When a crankshaft workpiece has to be reground, a crankshaft chuck, similar to the headstock spindle chuck, is introduced. In this case, the controls for crankshaft bearing offset takes place by the same tape reader, which shifts the headstock chuck within the same magnitude. The system in the above paragraph is connected to light indicators on the control panel to allow the operator to ascertain the machining process. The tailstock is used in different machining functions and may be provided with a remote control unit to reduce the operator's movement from the tailstock to the main control panel. Figure 5, Tailstock Sectional Details. Tailstock Parts. 1. Attachable chuck, clapper box socket. 2. Turret 6-way tool post. 3. Clapper box tool holder. 4. Cavity for electro-hydraulic ratchet tool selection. 5. Vertical feed hand wheel. 6. Lead screw. 7. Ram frame webs. 8. Ram case, cast iron. 9. Hydraulic barrel. 10. Piston determining the length of the ram. 11. Piston rod. 12. Linking member. 13. Dovetail slide block. 14. Pivoted joint. 15. Boring speed varying unit by a split pulley system. 16. L. Guides for ram. 17. V-belt, sectioned. 18. Split pulley plate. 19. Powerful motor 20 to 30 kW. 20. Shaping function V-belt. 21. Split pulley adjustment collar. 22. Manually affected speed varying fork. 23. Driven split pulleys. 24. Universal coupling joints, heavy duty. 25. Slide shaft assembly. 26. Universal rotation gearing cam assembly. 27. 40T driver gear. 28. 80T driver rim gear. 29. 20T idler. 30. 10T gear. 31. 20T gear. 32. Heavy duty, rigid triple start worm. 33. Loose pivot connection. 34. Sliding guides for the main pivot. 35. Compression spring of calibrated strength. 36. Angular reciprocating. 37. Sliding link rod. 38. Tail workpiece spindle driving shaft. 39. Electro-hydraulic clutch. 41. Compression spring to permit fluctuation. 42. Interlocked half, nut for worm. 43. Remote hydraulic mechanical gear pump. 44. Primary hydraulic reserve. 45. Fluid terminal connection. 46. Fluid terminal connection for the return pipe. 47. Electro-hydraulic selector fork. 48. Speed, step up, step down, unit. 49. Main pivot sliding mount. 50. Piston rod to pivot sliding mount block. 51. Hydraulic fluid charging chamber. 52. Piston. 53. Charging fluid terminals. 54. Discharging fluid terminals. 54. Shaping universal rotation worm. 55. Reciprocating half nut. 56. Reciprocating bar, 57. Transition fit pivot stud. 58. Tailstock transversal hand wheel. 59. Miter bevel gear and rack pinion mechanism. 60. Chuck cam lock flange. 61. Spline spindle. 62. 40T spur gear, driver. 63. Shifting collar with broached boss. 64. Spur gear, driver. 65. Fixed work spindle. 66. Hydraulic gear pump _. 67. Reciprocating pivoted link. 68. Angular reciprocating. 69. Worm. 70. Selector fork rod. 71. Section V-belt. 72. Auxiliary speed varying device, shaft. 73. Hand wheel for speed varying device. 74. Motor. 75. Shaping auxiliary speed varying device. 76. Driver split pulleys. 77. Hand wheel for speed varying device. Milling head. The milling head is an essential machine part and has been constructed with a power source, motor, that drives most of the milling functions. The mechanism incorporates a variable speed pulley system, which is also equipped with a speed monitor. Power is transmitted via the speed reduction mechanism to the broached spline shaft assembly designed to permit vertical quill traverse. The transverse traverse mechanism is a pinion rack type and derives power from the unit's work spindle via a reduction transmission set of worm gears to a ratio of at least 1,000th part of the work spindle's rotation. It is manufactured with an engagement electromagnetic clutch of friction type. Both the approach and return motions are rapid and up to a ratio of 1/10 of the working spindle speed. Work vertical spindle leads to a pair of miter bevel gears. This assembly projects the drive to the horizontal milling arbor, extending to an external flange, for mounting the grinding wheel. The prior described assembly also swivels the vertical spindle and is designed to be lockable and at the same time hydraulically adaptable. A quill spindle is provided with an automatic tool locking mechanism that allows an entirely automatic working cycle for vertical milling functions. The traverses along vertical spindle coordinates are hydraulically actuated and have been provided with a dovetail guide assembly to ensure the working stability of the tool head. Telescopic covers are provided to protect moving parts from easy access to dirt and human interference. Including the already specified vertical traverse, the unit has several other coordinate axes. The longitudinal milling traverse is provided by the headstock cross slide, wherein the milling ram executes its crosswise movement. The feed is powered entirely hydraulically and provided with an absolute numerical form of measurements. During specified functions, the longitudinal motion is adapted for incremental numerical values. Milling head transverse traverse works by means of a pinion rack assembly and is therefore programmed absolutely or incrementally. The milling head facilitates tool exchange motions. Its electrical circuit is available with transducers enabling the tape reader to select the tool on demand. Subsequent punched tape information is converted into actual approaches to the tool magazine within which a set of function tools are held. The system is designed for end millers only. On the other hand, in some special cases, more than one horizontal cutter can be fixed on the arbor, for machining components that require more than one type of tool. Consequently, the memory will have to be pre-programmed to perform the operational positioning of the cutting tool set. Profile tools, hobs etc., are also held on the horizontal arbor. An extension, tapered, arbor flange projects from arbor support brackets that serve for mounting heavy-duty grinding wheels for crankshaft grinding operations, for cooperative use of the milling head. For this particular purpose, both tailstock spindle and headstock spindle replaces the use of special universal grinders. The above described process may be designed for absolute numerical control. Figure 6, Milling head sectional details. Milling head parts. 1. Worm wheel assembly for speed reduction. 2. Web. 3. Rack, pinion traverse mechanism. 4. Milling head aligning guide. 5. Milling head saddle. 6. Loose pivot. 7. Split pulley. 8. Driver spur gear. 9. Spread monitor cavity. 10. Flexible fork joint. 11. Driven spindle, stepped. 12. V-belt. 13. Universal electromagnetic selector. 14. Selector collar. 15. Electromagnetic device casing. 16. Stabilizing bracket. 17. Stabilizer locking lever. 18. Dovetail guides. 19. Speed varying fork rod 20. 40 T spur gear. 21. 30 T spur gear rotating shaft. 22. Bearing. 23. Ratchet mechanism. 24. Ratchet coil spring. 25. Hydraulic telescopic servo feed barrels. 26. Bearing roller type. 27. Horizontal arbor ram. 28. Cast iron, hardened bracket. 29. Dovetail guides. 30. Sliding arbor support bracket. 31. Arbor locking screw. 32. Spline shaft assembly to permit displacement. 33. Telescopic covers. 34. Vertical quill support. 35. Swivel quill bracket. 36. Tapered, splined arbor alignment. 37. Tapered, splined quill. Tool magazine and speed control. A maximum of 10 end millers is held inside the tool magazine that is situated vertically below the milling head vertical spindle. The tools are arranged with code reference, serial numbers, that enable an entirely automatic selection of tools within the pre-programmed range. The resultant motion of transverse traverse, longitudinal traverse and vertical spindle traverse enables the selection and exchange of tools. The automatic spindle tool locking mechanism enables full gripping of the tool, while it is still capable of releasing the tool once an approach motion is made to the tool magazine to change a tool. Used tools are stored provisionally on a stationary type structure and cater for retooling motion by the milling head only. Thus, easy monitoring for entire tool exchange travels is facilitated. Figure 7, Tool Magazine and Gripping Sectional Details. Tool Magazine and Speed Control Parts. 1. T-slotting mill. 2. Tool release ejector. 3. Hydraulic ejector piston. 4. Charge pipe terminal. 5. Discharge pipe terminal. 6. Vertical milling spindle. 7. Cycling tooling fixture. 8. Tool release ejector. 9. Tapered trigger tool release. 10. Compression spring-loaded tool lock. 11. Morse tapered spline shank. 12. Compression spring. 13. Dovetail end mill. 14. Spline. 15. Forming T-mill. 16. Magazine tool stabilizer. 17. Inverted dovetail mill. 18. End mill centered stand pads. 19. Magazine bracket. 20. Stand pad. 21. Loose tooling fixture. 22. Diametrical spline fixture. 23. Expanding flexible tool releaser. 24. Tool section. Speed monitor. The speed monitor is designed to meet the needs for automatic speed exchange during an automatic cycle. It reduces the rate of automation interruption, which would otherwise change the control system to semi-automation. The design of the speed monitor is identical for every monitored unit, with differences in speed rating only. The speed monitor consists of a semicircular hydraulic cylinder within which a piston travels when the cylinder is charged with hydraulic fluid. The piston rod is also semicircular and is pivoted to semicircular rim gear to which a set of train gearing is like to increase the speeds of rotation, resulting in complete revolutions of axial lead screw advances. The axial lead screw displacement shifts the drive belt. In the case of split pulleys, the lead screw is replaced with a worm shaft that makes several desired turns to alter the position of the varying fork. Speed monitor parts. 1. Belt shift alignment shaft. 2. Sliding member. 3. Plastic finished, belt accommodating bracket. 4. Belt portion. 5. Belt's back view. 6. Plastic liners. 7. Fork bracket. 8. Bracket lead screw nut. 9. Triple start screw. 10. Mounting flange. 11. Section of spur gear number 20. 12. Hydraulic piston rod in number 22. 13. Elevation of semicircular hydraulic fluid cylinder. 14. Hydraulic fluid charge pipe. 15. Hydraulic fluid return pipe for discharged fluid. 16. Lead screw drive gear 30T. 17. Lead screw stud. 18. Spur gear 20T. 19. Hydraulic drive piston barrel, semicircular. 20. Semicircular spur gear 100T. 21. Projection trigger, fixed to node 20. 22. Solid, steel semicircular piston rod. 23. Idler gear 60T. Carriage. Machine carriage derives its power from lead screw rotations by means of a triple start worm gear mechanism. The worm gear is connected via a set of train gearing which participates in converting the lead screw rotation into traversing feeds of working motions. The feed derived from the lead screw is converted into the pinion rack transverse traverse mechanism of the carriage. Numerical control adaptation is linked to the pinion rack assembly to enable measurements along respective coordinate axes in the desired numerical form. An electro-hydraulic locking device is connected to the carriage to allow disengagement of pinion rack assembly while locking the carriage once the origin of a coordinate axis is reached. Any subsequent related motion by either the cross-slide, longitudinal traverse, or rotary table selection occurs by engagement of the lead screw drives by the action of electromagnetic clutches of conical friction type. Measurements of an operation datum are sensed during a periodical interval when the electromagnetic field is in force and tabulated in terms of the lead screw pitch and speed. The radial slide worm gear mechanism is enclosed within the cross-slide casing. Rotations of the worm are varied according to the angular velocity of the spherical contouring tooltip. This contouring process is made possible by means of carriage cross-slide feed. Radial tool position is selected according to the radius of the spherical profile being machined. The worm is driven by means of broached and spline shafts permitting cross-slide longitudinal displacement. The same power shafts cater for rotary table indexing. Therefore, an electromagnetic clutch selects the working part in receipt of information from the tape reader, command memory. Cross-slide traversing motion proceeds along with the extension guides of the tilting elevating table. Figure 8, Carriage sectional details. Carriage parts. 1. Worm wheel transmission. 2. 30T spur gear. 3. Rack pinion assembly for carriage traverse. 4. Pinion can either be driven by hand or by screw drives. 5. Compound slide lead screw. 6. 6-way turret tool post. 7. Electro-hydraulic mechanism for tool selection. 8. Rotary table. 9. Cross-slide lead screw. 10. Angular tilting elevation table. 11. Worm, wheel tilt mechanism. 12. Table tilt hand wheel. 13. Table swiveling mount. 14. Hydraulic feed piston for vertical table displacement. 15. Machine bed solid casting. 16. Stabilizing webs. 17. Longitudinal table, elevating hydraulic drive. 18. Broached bore, friction electromagnetic clutches. 19. Spline shaft for radial and rotary table drives. 20. Cross-slide lead screw. 21. Conical friction, electromagnetic clutch. 22. Tension springs for relieving quick return strokes. 23. Transverse traverse hand wheel. 24. Cross-slide, longitudinal, hand wheel. 25. Radial slide rotary table hand wheel. 26. Reciprocating flange for cross-slide. 27. Reciprocator stylus. 28. Conical relieving cam. 29. Single spline on screw worm drives. 30. Electromagnetic nuts for screw cutting. 31. Reciprocating flange for the cross-slide. 32. Dovetail guides for relieving parts. 33. Relieving part. 34. Adjustable stylus holder. 35. 30T gear. 36. 40T gear. 37. 50T gear. 38. Miter gear. 39. Claw clutch assembly electromagnetically actuated. 38. Initial bevel gear transmission. 39. Duplex chain and sprocket wheels. 40. 20T worm gear. 41. Single start worm. 42. 40T gear. 43. 60T gear. 44. Spur gear with conical friction clutch. 45. Idler gear. 46. Spur gear with conical friction flange for clutching. 47. Spur gear. 48. Bevel gear to the rotary cam drive. Carriage auxiliary tables. The carriage has two auxiliary tables. An elevating shaping table lies along with the carriage saddle in the longitudinal direction. This table elevates hydraulically with its y-axis measurements taken in terms of cubic millimeters of fluid charged into the cylinder. Complete measurements are in this case tabulated in terms of fluid velocity with time when the electro-hydraulic valves are active. The elevating cylinders lie beneath the saddle in the respective cavity. The tilting table elevates by means of the above-described principle while tilted mechanically during setup. When boring the engine blocks, it can be tilted by an electro-hydraulic mechanism. Carriage reciprocating unit. The carriage is provided with a relieving unit that derives its power from the lead screw. A duplex chain assembly transmits power to the conical rotary cam. The cam facilitates the relieving effect of the unit. Tapered cam is intended and designed to meet the varying range of relieving depth within the required range. The longitudinal traverse lock nut, in such case, is disengaged and the cross-slide box is connected to the reciprocating rod equipped with a spiral spring for tensional loading and rapid return strokes. The relieving positions are indexed as a ratio of work spindle rotation to screw drive velocity. Carriage turret tool post. Above the radial slide is a compound slide that encloses the turret tool selection mechanism. The turret tool post accommodates 6 cutting tools and has a hexagonal structure with self-centering devices for the cutting bits. Selection of the required tool in terms of tool serial number is decoded by the command memory via code readers. The shifting mechanism works hydraulically, the clamping of the pre-selected tool is automatic and the mechanism operates by means of a ratchet wheel assembly. The selection trigger is hydraulically actuated while it counterlocks the ratchet claws after a turn of 60 degrees, subsequently changing the position of the turret tool post and hence designating a new working tool. Figure 9, Compound Slide and Turret Tool Post Detail. Turret tool selection. Based on a different working principle, the turret tool only uses the 6 tools selected for any working stage. For immediate selection, the arrangement of the tools on the hexagonal tool post is based on the operation sequence, making use of every exchange of tool position provided by the NC-controlled hydraulic trigger. The revolving action of the turret ratchet is unidirectional, thus, clockwise and works in a manner compelling the program to be of analog rotary coordinate axis type. The turret tool post is strong and rigid when locked in position. This reduces tool vibration that may cause machining inaccuracy. The turret mechanism is enclosed inside the compound slide cavity. The compound slide is mechanically activated due to its limited purposes. Turret parts. 1. Cross-slide lead screw. 2. Detachable half nut. 3. Detachment lever. 4. Spline shaft transmission for the displacement of X-axis. 5. Compound slide handwheel. 6. Lead screw. 7. Tool bit. 8. Tool bit holder. 9. Tool centering device, worm gear actuated. 10. Worm shaft. 11. Turret manual turn lever. 12. Worm single start. 13. Turn base. 14. Ratchet wheel, with face and rim relief. 15. Swivel stabilizer for radial slide. 16. Cross slide guides. 17. 90T worm gear. 18. Worm shaft. 19. Hydraulic fluid charge pipe. 20. Hydraulic fluid discharge pipe. 21. Piston rod and trigger mounting. 22. Triggering guides. 23. Ratchet spring-loaded spike lock. 24. Torsional spring. 25. Ratchet relieve tooth. 26. Compound slide case bracket. 27. Face relieving tooth. 28. Left-hand spike. 29. Piston. 30. Pivot. 31. Worm gear section. 32. Worm single start. 33. Saddle. 34. Half nut. Indexing. Indexing is a computed means of automation without which gear cutting is not possible on this machine. The design and position are novel and advantageous. The system is equipped with dividing indexing, differential indexing, spiral indexing, and even hypoid gear indexing. The indexing system is adapted to the numerical control system for simultaneous operation. The unit does differential indexing by adaptation to the cutting transverse traverse and vertical traverse of the milling head. A pair of partly idle worm gearing is selected by the command memory depending on the working stage of operation. One worm gear is engaged for dividing indexing while the other is engaged for differential indexing, for spiral, helical, axial, hypoid, epicyclic. The unit functions only on an adaptation basis. Figure 10, Mechanical Indexing Sectional Details. Indexing Mechanism Parts. 24. Brass split bearings with a special lubricant. 25. Work spindle. 26. Duplex chain on sprocket wheels. 27. Electromagnetic, reversal friction clutch for indexing. 28. Robust electromagnetic armature. 29. Very strong heavy-duty electromagnet. 30. Soft iron core for coil wounding. 31. Shifter clutch plate fork. 32. Dividing indexing worm wheel assembly. 33. Universal, heavy-duty electromagnetic clutch fork. 44. Rack. 45. M-head casing. 46. Quadrant slot for stabilizer advancement. 47. Recess slot for lock, lever. 48. Mentioned in number 44. 49. Swivel head. 50. Till spindle. 51. Head swivel pad. 52. Bearing. Figure 11, NC electro-indexing circuit and sectional details. Indexing mechanism parts. 34. Brass split bearings with a special lubricant. 35. Work spindle. 36. Duplex chain on sprocket wheels. 37. Electromagnetic, reversal friction clutch for indexing. 38. Robust electromagnetic armature. 39. Very strong heavy-duty electromagnet. 40. Soft iron core for coil wounding. 41. Shifter clutch plate fork. 42. Dividing indexing worm wheel assembly. 43. Universal, heavy-duty electromagnetic clutch fork. 53. Rack. 54. M-head casing. 55. Quadrant slot for stabilizer advancement. 56. Recess slot for lock, lever. 57. Mentioned in number 44. 58. Swivel head. 59. Till spindle. 60. Head swivel pad. 61. Bearing. Figure 12, Hydraulic crankshock sectional details. Hydraulic crankshock parts. 1. Head workpiece bracket. 2. Stud spindle. 3. Stud gear. 4. Stopper. 5. Torsional spring. 6. Crank spindle fluid charge pipe. 7. Crank spindle fluid discharge to master cylinder. 8. Work chuck fluid pipe to grip jaws. 9. Hydraulic circuit flange. 10. Crank block slide cavity. 11. Hydraulic fluid pipe to chuck jaws. 12. Piston for a hydraulic shift of chuck. 13. Piston spindle. 14. Jaw hydraulic piston. 15. Grip jaw. 16. Fluid diversion chamber. 17. Jaw mount, block. 18. Jaw piston rod. 19. Fluid grooves. 20. Chuck cam lock mounting flange. 21. Fluid strainer. 22. Fluid charging cylinder. 23. Bearing. 24. Work spindle. 25. Roller bearing. 26. Swivel bracket. 27. Piston spindle. 28. Revolving rim. 29. Crankshock slider. 30. Slide for jaws. 31. Chuck case. 32. Three-step jaws. 33. Crank bracket. 34. Piston spindle. 35. Mentioned in number 12. 36. Hydraulic drilling. 37. Fluid circuit pad. 38. Section of the rotary rim. 39. Fluid bore. 40. Crank block front detail.